So the final presentation of today is from Carola, and Carola is a professor at the University of Cambridge. And her background has mostly been in imaging and all of these other things, but she has an enormous width, and she's done optimization, and recently she's been doing quite a bit of machine learning as well. And of course, when Carola tries something, she doesn't just do it a bit, she does it properly. And I recently saw you had the best paper award from ICML, which is outstanding. So it's very impressive how quickly and how much you've actually started contributing to the field of machine learning as well from imaging. And today, I think we'll be hearing even more of this kind of intersection between imaging and machine learning, which is quite exciting. Thank you.
Thanks a lot, Jonas. And you know, all these success stories are really due to the great people I'm working with. So yeah, it's just that there are wonderful people around me. Okay, so modern mathematical imaging is really all about combining mathematical modeling, analysis, with data-driven components coming from machine learning to solve inverse imaging problems, image analysis, image processing problems. So the art somehow is in developing new techniques in this realm to do it in a way such that you get the best from both of these worlds. And so this is something I would like to talk about in this presentation, and give you a few examples of where we got, well, let's say close maybe to such an ideal optimum. Okay. So before I start, maybe a bit of background, just so you understand also the viewpoint that I take, so the background that I'm coming from. So I'm, as Jonas said, I'm professor of applied math in Cambridge, where I had the Cambridge Image Analysis Group. And I'm also the director of two centers in the Faculty of Mathematics in Cambridge. One of them is the CCIMI, the Cantor Capital Institute for the Mathematics of Information, which really is a research and research training institute for the mathematics of data science. So we're always looking for skilled and passionate PhD students, a bit of advertisement here. And then the other one is the CMIH, the Center for Mathematical Imaging in Healthcare, which is a multidisciplinary research center between mathematicians, statisticians, engineers, physicists, medical researchers, and clinicians to develop new medical imaging, image analysis processing techniques. Okay, so this is the Cambridge Image Analysis Group, or short CIA. We are about 20 people. Half of us are postdocs, the other half PhD students. And you can see that work in the CIA is fun, at least in our CIA. We are very fortunate to be sponsored by research council funding, private trust funding, as well as several industrial sponsors. So what do we do in the CIA? We develop new mathematical methods in the context actually of, again, what Jonas raised before, applied mathematics in general, applied analysis actually in particular, so partial differential equations, variational models, optimization, and machine learning. And we develop techniques to solve quite a wide range of image-related tasks, from image reconstruction, from indirect measurements like in medical imaging, to image restoration, image segmentation and classification, motion estimation and object tracking, just to name a few. And so we develop these techniques always very close to real-world applications, again, ranging from photography, remote sensing, biomedical imaging, art restoration, forensics. Actually, application-wise, it's quite broad. Okay. So the presentation is somehow structured like this, that I'll start with a more philosophical introduction, and then I give you 2 examples of such hybrid combined mathematical modeling, machine learning approaches that came out of our group in the last couple of years. But I thought it's quite important to motivate this first and to give a bit of an idea of what the issues and the challenges are that we are facing in mathematical imaging. And here I'm borrowing a concept, a characterization that IBM used a couple of years ago for big data. What is big data? And so they published this characterization of the 4 V's of big data. So I'm now giving you the 4 V's of imaging data. Okay, so the first V is volume. Imaging data is huge. It's large scale, high dimensional, and so this is a huge computational issue, of course. Variety. Again, thinking of all these applications that I've listed, the images you might appreciate that come out of these applications vary a lot, right? So, and here you just have a few examples. This is a histology image. This is a CT image. This is a photograph of a historic illumination in a manuscript. And this is just a natural photograph. So there is quite a diverse set of different images. And so if we want to automate, if we want to develop methods which can deal with all of this, you might appreciate that this is challenging from a modeling point of view, and might also be challenging if we think more in the data-driven context to translate approaches between those different types of images. Okay, velocity. Imaging data is acquired at increasing speeds. And so the more imaging data we acquire, the faster we acquire it, the faster also our processing abilities should get. And so again, this is a huge challenge to process this in kind of real time. And then everyone, I guess, who has dealt with real data in general is also aware of veracity. So imaging data is messy in the sense that it's noisy, it's imperfect, it can have other kind of artifacts. And so all the methodologies that we develop to analyze such data, of course, need to be able to be robust to such corruptions. Huh? Okay. Okay, but in a way, mathematical imaging is not so much about the data. I mean, we need to understand the data, but it's about extracting information from this data. And in mathematical imaging, this information can come in all kinds of shapes and forms. Here are just 3 examples. So at the beginning, when I told you about the CIA, I mentioned motion estimation as one particular task. So what you see here is a statistic of directions, of average directions that have featured in a video of a particular length, okay, where people are moving around. In which directions are they moving? And I'm drawing you a histogram of what the directions that were featured in this video are. So you might want to know what is the trend in a video or something like this. So this is a particular visualization of something like this called the Rose diagram, where here the histogram is plotted against the angle. Okay, so this is one type. So you might want to quantify something in images that you then put into statistics. Another type of information could be classification. You have an image and you want to divide this image into different classes. In this case, this is the underlying image here is a hyperspectral image, and we want to decompose it, classify every pixel into a different land cover, different type of vegetation, let's say. Okay, and bit of a related task is the last one, which is segmentation. So here I have an image and I want to outline in an automated fashion objects in this image. And I want to do this maybe because once I've outlined them, I can measure shape, I can count how many there are, things like this, okay? Right, so these are just 3 examples. There are many, many, of course, as you can imagine, and I'm sure you have some examples in your mind yourself. So now we talked about the data, we talked about what we want to extract from this data. So how do we do this? And here the 2 paradigms of mathematical modeling and machine learning come in, and I name them here as knowledge-driven, so something that we can model, and data-driven, something that derives the model from the data. Okay, so let's talk just briefly about these 2 paradigms. So knowledge-driven imaging has actually a very long tradition. And I would say has been the go-to solution almost until the rise of deep neural networks recently. This has been extremely successful and has given a lot of food to mathematicians to analyze these new models that appear in this context. Okay, so knowledge-driven imaging is based on mathematical models and physical principles. And basically, it always arises when you have data, you have imaging data, and you have the information you want to extract from this imaging data. And the first thing you need to be able to do is to write down an equation for how this information is related to the data. And then you have to write down another equation that helps you to extract this information from the data. Okay, so this is the basic idea of this mathematical modeling paradigm. And these type of equations that can extract information from the data can come in various, again, forms. They come in the form of nonlinear PDEs. This is, by the way, also my original background. I did a PhD basically in PDEs. Variational models, where the information you extract is modeled as a minimal energy state of functional. And something that is also quite dominant in this mathematical modeling paradigm is the idea of characterizing the information, the solution, for instance, to the PDE or to such a variational model in terms of sparsity. That you say you can represent this information in some kind of basis or dictionary in a sparse manner. You have a simple representation that you then use to reconstruct this information. Okay, and so multi-resolution sparsity constraints come into this context. Okay, so this is the knowledge-driven paradigm. Now, the data-driven paradigm says, I don't have a mathematical model that relates my information to the data, and also I don't know how to write down an equation that extracts this information from the data. So what I want, but on the other hand, I have a lot of examples of paired data, okay, and corresponding information. I have a lot of examples of the kind of information I want to extract from this data. Using this now, which is called the training set, I start with a highly over-parameterized model, for instance, a neural network. And I want to train the model, this neural network, I want to optimize these parameters by means of fitting the examples of the information that I have in order to get my image processing model, okay? Okay, so now what are the advantages and disadvantages of both of those? Because if we want to combine them, right? Or, I mean, why do we want to combine them? Are we happy maybe with one of those, right? And probably we aren't. And then the question is, what should we take from each of these paradigms? Now, starting with the knowledge-driven paradigm, one huge advantage before I go to the disadvantages is that it's a universal concept, okay? So it's an equation. You can solve this for any kind of image that you get if it fulfills the requirements that the model is well posed. Well posed is yet another thing. If we write down a mathematical model, we can prove properties about it. We get solution guarantees, and this is very closely linked, of course, to robustness of these methodologies with respect to noise and other imperfections in the data. There are also a lot of disadvantages. And so let me raise a few of them. So as I said, this is just a reminder again. In the mathematical modeling paradigm, I start with a model that relates the information I want to extract, that is here called U, to the imaging data that I've measured, which is here called Y, and I assume that there is a process that connects the two, which is this capital T. Not in all imaging applications. I can write this down as explicitly as this. I mean, think about segmentation or classification or things like this. But it's a good kind of abstract model to have in mind when I'm talking about this, okay? And then little n just stands for random corruptions, okay? So I start with the data model, and then I come up with a well-posed approach to compute this information U from the data, okay? And these type of relationships here are sufficiently, usually in real world applications, sufficiently complicated such that you can't just solve this equation. Well, I mean, here you have random corruptions. You wouldn't anyway, you would not be possible, you would not be able to do this anyway. But even without those, these processes, these operators T, are usually the inversion of those is ill-posed, so you can't just solve this equation. So one way around this are mathematical approaches like variational regularization, where you phrase your solution as a minimizer of an energy functional. We have seen this on the previous slide, right? So here I'm just giving you an example. And just to have this in mind also for what I'm showing you later, these variational models usually consist of two components. One captures the data model, okay? The model I have for the data and the information. And the other one captures a term which turns this ill-posed problem into a well-posed one, which is usually capturing some prior information you have about the type of use you want to compute from the measurements. And it's called regularization because it's in the classical functional analytic type of approaches. It's adding regularity to your solution. Here, in this case, for instance, by minimizing the L1 norm of the gradient of U, which is also called total variation regularization. Okay, and which also, going back to the sparsity, models sparsity of the gradient of your solution of the information you want to extract, which means the gradient, the derivative of the image should be 0 in almost all places and just non-zero in a few characteristic places, which are the edges where your gradient is large. And this type of prior information has proven to be very, very successful for many, many imaging tasks, although it sounds totally simple. Anyway, so what are the disadvantages of these type of approaches? Well, first of all, it's a computational challenge. Okay, I've talked about nonlinear PDEs. Now here you see these optimization problems. Again, I've told you that Y is usually very high dimensional, large scale. These capital T's, these forward operators, are also costly to evaluate. And then here, even worse, I've made things even worse by having this non-smooth regularization here. So you can't just do, in order to optimize this, your plain vanilla gradient descent or something like this, because you can't even differentiate this. Okay. Okay, so there's a computational challenge. Of course, now look at all these different types of images. There is a no one-fit-all solution. So mathematical modeling of these, in particular, the type. So I said before that this regularization chooses the type of solution you want to reconstruct that fits the data model. Now, characterizing these type of things that you have here versus characterizing structures that you see like in this image, you might appreciate that they're very different, right? And so there is a no one fit all solution, and very closely linked to this, there are also no model-based solution that exists that can capture all of these little fine details in the images that you see. Okay, there are approximations. Okay, so it makes it hard to model everything. Okay, so these are the disadvantages of the model-based approach. So what are the advantages and disadvantages of the data-driven approach? So data-driven, now actually starting with the last point, the cool thing about doing something data-driven is, depending on the complexity of your parameterized model, where you then fit the parameters to your training data set. Let's say with a deep neural network, you have a very, very highly over-parameterized model. The cool thing about this is that you can very nicely adapt to your training set. And so you can actually model a lot of complex things, right? So this is definitely the advantage, and therefore machine learning approaches like deep neural networks are known to be very good in modeling prior information, where this prior information is given by the training set. Now let's go again to the limitations, to the challenges. And again, lots of these challenges we have seen in this workshop and will be seeing also in the next days, which again will give a lot of mathematicians in our community food for doing some nice mathematics, but it's really necessary to do this. So what are the disadvantages? It's a black box. I mean, if you have millions, billions of parameters, it is a black box. I mean, there are attempts to try to make this a bit more interpretable, but overall it's a black box. Just compare it with the PDE that I've written down. Such a PDE we have more or less under control. Modulo, what we can prove about it, of course. With a neural network, it's hard. Theoretical underpinnings there are more and more, and this is why we are having the workshop, but there are a lot more challenges and a lot more open problems that still need to be solved. And we have seen, for instance, in the last talk as an example, these adversarial perturbations. Yeah, so this is worrying for if we want to develop something that is robust, a methodology that is robust. We don't want that someone can perturb our input and then the network gives us something crazy. The other thing is that neural networks, if you train, okay, a neural network, I'm now talking about neural networks mainly here. If you train that with training data, then it's very good to then you take it away and you give it new data that is similar, right? So it's very good at interpolating, giving you predictions for which it can interpolate between the things that it has seen before. They're not good at extrapolation, and this is not good, because first of all, it means you need huge training sets. And even if you have huge training sets, of course, in particular, thinking about scientific imaging, you might not be able to capture everything because you might have not seen something before. Maybe you want to use imaging to discover something new. So things like this are worrying. Now, this is just a summary again, a table of, summarizing what are the advantages and disadvantages of both. And now let's put this in context with the imaging requirements that we have in the real world, okay, in the wild. Now we started with the 4 Bs. Imaging data is large, it's complex, it's messy. And so the requirements onto the image analysis processing inverse problem solutions are, what are they? Let's think a little bit about this. So And here you might even add a few things. When I prepared the slides actually yesterday, I thought I should add, but I didn't add some other things. But so one of them is, for instance, of course, the robustness to data corruption. We need to be robust to noise and imperfections. We've said this before. Extrapolation, in particular in the context of medical imaging, scientific imaging, is also important, both because we have usually small data sets in practice, and also because we want to discover new things. On the other hand, we also want something that is sufficiently accurate. And this is something that deep neural networks are very good in, to meet diagnostic, prediction, planning needs, whatever the application, what the needs are of the application I want to solve with this. And we want the methods to be computationally affordable. So ideally, we want something that brings together all of these things: computational affordability, expressivity, or expressivity, rigor, interpretability, and so on. Interpretability was the one thing I wanted to add to this list before. No? Okay. Okay, so what I want to do in the remaining 10 minutes, I guess, is to give you just two examples of something that is still not optimal. It's not totally part of the table I've shown you before, but we hope that we are getting close. Okay. And the first example is from medical imaging. Okay. So here, the problem we want to solve is an image reconstruction problem from indirect measurements. So the idea is that I have imaging measurements, which here in the context of computed tomography are noisy, incomplete projection data from the actual image I want to reconstruct, the image density I want to reconstruct. Projection data in this case in the form of the X-ray transform, so integrating over the X-rays that cross the volume you're imaging. So based on such measurements, again, which are noisy, incomplete, I want to reconstruct an image like this. And again, one thing I could do is to go back to my variation regularization idea, is something that has been widely and very successfully been used for many of these problems, and solve it with this. Yeah. One thing that we did in this context of variational regularization is to insert a data-driven component into the place which is usually the hardest to model. And this is the prior information. The prior information about the type of images I want to reconstruct. And this is given by the regularization. So something I'll show you now is how can you solve a variational problem or set up a variational problem where you use your data model. Okay, so the data model I want to keep, I'm kind of certain or kind of okay with the approximation that I make in my data model. And what I want to set free in terms of parameters, the regularization. So first of all, just to give you also a picture in this context, what is the effect of this regularization? So Shubo, again, thank you very much for providing this to me. So what you see here is a setup where the type of image I want to reconstruct is very simple. So actually, this is a setup where a model-based regularization like the total variation is definitely okay. But just to show you the effect, this is in the context of sparse view CT, which means I have this projection data, but just from 22 angles. And what you have here, this is simulated. Okay, so I've simulated these measurements that we have seen before here. I've simulated them from the image. And now from these simulated measurements, I want to reconstruct something that looks close to the ground truth. Now, what you see here is what is called minimal norm solution or pseudo inverse, which is basically minimizing this least squares fit between the model and the measurements with an additional minimal norm constraint. Is also a certain form of filtered back projection. If some people know about filtered back projection CT. So if you do this, you don't get something that looks very nice. If you add regularization now to this minimization problem, and regularization now in the form of a prior information that is very close to the image that is behind these measurements, then you get something that is almost perfect up to a bias that you get in terms of contrast loss. Okay, of course, the world doesn't look like this in general. So something that the world doesn't look like this in general motivated us now to come up with this learned prior, with this learned regularizer. And the idea is now, instead of taking the total variation as this regularizer, we parameterize this regularization term, which takes as an input an image, okay, and gives us an output, a real value that tells you, just going back to this, that tells you, I'm minimizing this, right? That tells you how good this image is in terms of a solution, of course, together with a fit to your data model. But basically how you should think about this is that for the type of solutions that I want to compute, this regularization term should be small. And for the type of solutions I don't want to compute, let's say solutions like this regularization term should be large. Okay, and this is really, now I'm telling you already how we train it. So we set up a network that takes as an input an image, and as an output, it gives you a real value. But how to train this? We need a loss function, right? So the first thing to think about is, how do we design this loss function? And so this, maybe I should have said this. This is joint work with Sebastian Lunz and Ozan Öktem. And it's really most of the work that I'm showing you is actually due to Sebastian. So Sebastian actually made this work. Okay, so what's the idea? So the idea is, the idea is to train the regularizer in a way that it differentiates between the things that it should penalize, should get rid of, and the structures that it should, the solutions, the images it should favor. And so how we do this, how do we set up such a training set? So we need training images from both sides, from the side of the good ones and the bad ones. Okay, the good ones, we can, if we start with a simulated training set, okay, we can just start with already reconstructed CT images, simulate crappy measurements, so sparse angle measurements and noisy measurements, and then reconstruct with, let's say, filtered back projection that before we have seen gives such results. And here in this, this is more low dose CT with more angles, gives you these kind of results. So what we now want to do, we create such a training set in this manner, ground truth images and filtered back projection images, and then we create out of those, so we create lots of samples from those, and we summarize them in two distributions, one that I call PR, these are the ground truth images, and one that I call PN, which are my noisy, corrupted images. And now I want the regularizer, again, so I'm trained the regularizer in an adversarial manner such that the regularizer is large for images like this and is small for images like this. And what I've just told you is, again, what I'm showing you now on the next slide in terms of an equation, more or less. Just focus with me on this equation here. So this is the loss function we are using. The only difference is that I'm optimizing here. So the regularizer, in this case, should be a maximizer of this difference here. Where the difference, of course, if I'm now optimizing this over neural networks, is that my F is parameterized here by a neural network. And I'm optimizing over the parameters of this neural network. And so the regularizer so this loss function is exactly set up by what I just said before. It should be, now let's see, I'm maximizing, so it should be large for images coming from the noisy distribution and small for images coming from the ground truth distribution. And yes, and maybe I should say, this is connected to the von Wasserstein distance. So we use the von Wasserstein distance between those distributions as a loss function. And the von Lipschitz continuity of the regularizer also comes in handy the moment we want to prove things about the approaches about the regularizer we have trained. Sorry, I've just distracted looking at the watch. Okay. So the summary is now this is again written down the loss function. The only difference is that instead of F, I've now taken psi theta as my notation for the neural network, because it's something that depends on parameters theta. And the constraint here I've added as a weak constraint as a Lagrangian to the loss function here. Okay, so I'm enforcing the von Lipschitz, and it's by enforcing that the gradient of the regularizer should be close to 1. Okay, so so we train the regularizer in this fashion. The neural network that Sebastian has chosen is just an off-the-shelf convolutional neural network. And then once we've trained it, we plug it back into our variational model, and then we solve it. Okay. And that's it. And then we minimize this with whatever you want. Okay. We just did gradient descent in this context. So the main message here is that in combining this model-based idea with the data-driven idea, namely sticking with a variational model and then plugging in the data-driven machine learning idea in terms of a regularizer, is that we have something that is adaptive, that models the prior information based on the training set, but on the other hand is something that we can handle mathematically. And maybe one more thing to say is that one downside of this to, let's say, total variation regularization is, of course, that this regularizer, if we just take a general neural network, is totally non-convex. One thing that we actually will put onto arXiv today or tomorrow is a convex version of this that we have been working on together with Shubho Mukherjee, Søren Dittmer, Zach Shumyalov, and Oza Nakdam. Okay, so just a few results. Just to show you how this works, we call this the adversarial regularizer. This is the ground truth. This is the reconstruction. So this is already a solution of my variational problem, okay, after I've trained the regularizer. Here, on the right is always the result for the adversarial regularizer. On the left, you see other types of reconstructions. Now, this is the filtered back projection. Of course, this is much worse than this. This is the total variation. Okay, so the total variation was the regularizer being the L1 norm of the gradient of U. And you can see, of course, that learning a regularizer pays off. And I'm not showing you all the numbers, but it also pays off in terms of quantitative reconstruction evaluation. Okay. Okay, so I guess, Jonas, do I need to finish?
Yes, I guess so, at least. There's no one after you, so we're not that stressed, but I think some people want to have questions, I guess.
Okay. So, okay, so then I'll finish. Let me just say one more thing. This combined approach appears in many different ways. One thing that I didn't tell you about that I would have if I would have time, is that we did something similar for classification, where we used the Peeler Blushen as the model-based component, together with a graph clustering idea where we use a small proportion of labeled data. So you have a small proportion of labeled data together with a model that propagates these labels to all the unlabeled data points. And again, this actually paid off quite nicely because you can do this with a very small number of annotations. Okay, so takeaway messages. So mathematical methods are really quite powerful, and they are rigorous, universal. They have lots of advantages. They're not very good in modeling prior information. They're not very good in adapting. Therefore, I mean, universality is in contrast to being very adaptive to different data sets. Machine learning, deep learning in particular, these very, very high parameterized models are very powerful as data adapters. So why not try really to combine them? And I really think that these hybrid methods are the future, lots of cool applications, and of course, many open questions in both theory and application. Thank you very much.